Thanks. I was actually telling Jonathan last night that when I was accepted to the PhD program at Davis, my letter actually started with, once again, we... so somebody had a sense of humor. The work I'm going to show you today is kind of a combination of things that I've been working on through grad school and through my postdocs, focusing largely on the properties of silicate melts at high pressure. So, as Jonathan said, I'm a postdoc, and in this season of job applications, right, you spend a lot of time thinking about what category your work falls in. And often, my work falls under solid Earth geophysics. But really, the part of the Earth I'm most interested in is the liquid parts. And in the Earth's crust and mantle, the predominant liquid phases are silicate melts. So silicate melts do share a lot of similarities with crystalline silicates. They're built of the same fundamental building blocks. So at modest pressures for high pressure mineral physics people, you know, up to about 20 GPa, the fundamental component is the silica tetrahedra that link up to form networks. However, silicate melts and also their frozen counterpart glasses are amorphous materials, and so they lack long-range order. And as a consequence of this, their physical properties are actually very different. And because their physical properties are very different, the techniques that we use to measure the physical properties of crystalline materials and the equations of state we use to predict their behavior generally don't work well for amorphous silicates. So silicate melts in glasses have play a major role in a lot of sort of broad, big science questions, like what controls the dynamics of volcanic eruptions? They also are the main means of transporting both heat and mass, and so play a major role in planetary differentiation. The presence of silicate melts can also drastically affect the rheology of the Earth's interior, and so has implications for our understanding of plate tectonics. And in my talk today, I'm going to get back to this idea and kind of talk about what we can understand for the role of silicate melts at the Lithosphere-Asthenosphere boundary. There's also, for seismology, for example, regions where there are low velocity zones, we also often attribute that to the presence of silicate melts. So understand the properties are really important to be able to actually constrain seismological observations. And then sort of going back, if we want to understand the dynamics of planetary impacts, especially ones where we end up melting large portions of the Earth, or how do we retain geochemical reservoirs, understanding the physical properties of silicate melts at high pressures is really important. And further, often silicate glasses and melts have a big role in technological applications, all of our smartphones, those sorts of things. So we often, for a wide range of reasons, want to understand how these materials behave at both high pressure and high temperature. So this is the equation of state. And what I'm going to show you today is that besides addressing some of these big science questions, there are practical implications for interpreting things like seismic velocities if we can actually constrain density and velocity of silicate melts at high pressure. Okay, so we're going to start at the very beginning. We're going to talk about the different states of matter very briefly. So we all know that on Earth, right, we have three states of matter: solid, liquids, and gases. We have really nice equations of state to be able to predict the behavior of solids, like the Birch-Moynihan equation of state, or gases with like the ideal gas law. And so silicate liquids share some property, or liquids in general, share some properties with both solids and gases. So like this example of a cat, which is technically a liquid because it changes its shape to fit the container, but has a fixed volume, right? They kind of, often how we think about liquids is that, oh, they're a really high density gas, or a really low density solid. And what I'm going to show you today is that this sort of thinking is fundamentally problematic, especially when we get into things like interpreting melt fraction from seismic velocities. So I'm going to start off a little bit by going back to the structure, just so that we're all on the same page, and the structural similarities and differences between glasses and melts, so amorphous silicates versus crystalline materials. Like I just said, they're fundamentally constructed of the same sort of building blocks. So this here is an example for quartz and silica glass, and you can see the fundamental right here building block again are these silicon atoms tetrahedrally coordinated by oxygen. And to a first order, they're actually very structurally similar, right? We have these rings in both of them of these polymerized tetrahedra. The thing that's different here is that crystalline materials have periodicity, which means that their structure repeats, and that breaks down in amorphous silicates. You actually have a lot of, once you move from your very local environment, you start to lose the ability to predict where atoms are. And just because many of us don't work on glasses and liquids, I'm just going to briefly tell you the difference here. So when you cool a liquid, right, there's some temperature, the melting temperature, where you would predict that you would crystallize a material, right? So this is volume as a function of temperature, and here we have a liquid coming down. When it reaches the melting temperature, you have a large volume decrease because the atoms are able to rearrange themselves into a repeating structure. It's the lowest pre-energy phase, and so you end up with a crystal that's down here. To form a glass, what you do is you actually you cool the liquid past the melting temperature without crystallizing. And so the atomic rearrangement slows down. And eventually, you're going to reach some temperature. This is what's known as the glass transition, where the atoms aren't able to rearrange on the time scales of observation. And that's when you form a glass. So the important thing here is that glasses are effectively frozen snapshots of liquids. And there's some information that we can extrapolate to liquids by understanding the properties of glasses. Okay, so this figure schematic here involves volume and temperature, but really what we're interested in is how silicate melts and how material properties change with pressure when we're talking about planetary interiors. Okay, so inside the Earth, we have a few ways to directly sample the materials that are there. One thing is we have volcanoes that are erupting, and not only do we know that there's silicate melts inside the Earth because they come out sometimes, but also silicate melts through eruptions are a means of transporting crystalline samples also to the surface. Another actual major player that I don't normally think about is that kimberlitic eruptions are also silicic magmas that bring samples to the Earth's surface. These are some of the diamonds from Graham Pearson. This middle image here where they're looking for inclusions. Really the holy grail, of course, is ringwoodite or something higher pressure and things with water. And these kimberlitic eruptions that are sampling the transition zone and bringing up mineral inclusions like we can see on the far image are really the deepest way that we can see into the Earth. And we can only sample the Earth where these eruptions are happening. So usually what we do to understand the properties inside the Earth, right, is we use geophysical observables, things like velocity. And the thing about velocities, seismic velocities, is really what you're measuring, right, is the travel time. This is a non-unique parameter. It's just telling you how fast or how slow something is. So to be able to interpret seismic observables, you have to couple it with mineral physics. And by doing that, we can see that things like the discontinuities and the global average seismic structure correspond to phase transitions in the Mg2SiO4 polymorphs. So a little shout out to UC Davis here, since I spent so much time there. What I'm going to spend the next portion of my talk telling you is basically amorphous silicates, much like this cow, are very weird. They don't follow the behaviors that we would predict based on crystalline materials, even though we usually use crystalline equations of state to model their behavior at high pressure. Okay, so let's start at Birch's law. So in 1960, Birch published this seminal paper, right, where he measured the compressional velocities of a wide range of rocks and minerals to about a GPa, and what he found is that there is this positive linear corollary between velocity and density for minerals of a constant mean atomic weight. And what that means is a constant mean, or a mean atomic weight, is when you take the molecular formula weight and divide it by the number of atoms. So most silicates are actually around 20 for this. And so what you can see here, so this is the silica polymorphs, quartz and coesite, and up here we have our friends forsterite, wadsleyite, and ringwoodite. And you can see to a first order, right, they lie along these lines of constant mean atomic weight, whereas you increase density, you know, whether it's through composition or through structural changes, you have this very predictable collinearity. And this is what's seen and predicted in equations of state like the Birch-Murnaghan or the Veneer. All right, so let's look at silicate melts. Oh, actually, we're going to talk about crystalline silicates for just a second more. So we can also see that this relationship holds when you compress, when you change density by increasing pressure in a single phase. And that's what's shown here for instatite as it goes through the ortho-instatite to clino-instatite phase transition. Okay, but if we look at silicate melts, what we can see is that regardless of their density here, they have a very narrow range of p-wave velocities, right? This is not what we would predict by Birch's law. And you can see here these lines where I've linked the crystalline and liquid phases. You would project, because these have lower density, that they should follow along sort of these sorts of trends. And you can see that really they're cross-cutting. And what's really interesting is that you can have this really wide density range and still have these very narrow velocities. Measuring the velocity of liquids at high pressure is challenging. So most of our velocity measurements for liquids are at 1 atmosphere. But we can start to look at glasses to kind of see how they behave to get some insight into the high pressure behavior of melts. So here are data for silicate glasses. You can see again, they're constricted to a very narrow velocity range. Similar to silicate melts, it's a higher velocity, but a very narrow range, regardless of density. And what's really interesting is that when we look at the effect of pressure on silicate glasses, what you can see is that as you increase density by increasing pressure, you have this very weak pressure dependence. Some are weakly positive pressure dependent. Things like basalt actually have a negative pressure dependence for velocity as you increase pressure. So this sort of weak pressure or density dependence is similar to what we see in silicate melts at 1 atmosphere and is in direct contrast to what we would predict for crystalline silicates. Okay, at high temperatures, silicate melts at 1 atmosphere also have regions of increasing density. So normally, what we have here is density, so increasing that way as a function of temperature. And normally, as you heat up a material, thermal expansion leads to a lower density. And that's what you see here. But between about 900 and 1700 degrees C for silica, as you increase temperature, you actually increase density. And what we've shown is that this corresponds to the existence of 2 polymorphic phases in silica. And these are similar to like the alpha-beta cristobalite transition. And so they're constructive of the same major units, predominantly 6-membered rings of silica, but we actually see a difference in the physical properties of the 2 phases, the bulk moduli and those sorts of things. Okay, at high pressure, it's been known for nearly a century. I mean, Richmond did his original work in 1925 and then had to rebuild the machine and got slightly better measurements. And these measurements still hold for silica. We know that there's this region where we have increasing compressibility with increasing pressure. So normally, right, when you think about a material, as you increase pressure, you reduce the volume, and so it becomes, and you compress the inner atomic potential, so it becomes harder and harder to reduce the volume further. And that's what's shown here for basalt melts. These data go through sink float, or this line goes through sort of the sink float data points, and it's what you would predict for crystalline equations of state. But you can see here that again, for basalt melt, just like silica glass, we have this region of rapidly increasing density on compression at modest pressures. Electrical conductivity also shows opposite behavior for crystalline and liquid silicates. So for crystalline silicates, as you increase pressure, the models back here most of the lines are models. Here's the actual experimental data highlighted in red. So we have conductivity as a function of depth. And as you increase density, as you compress a crystal structure, even going through phase transitions, what you see is that there is a increase in the conductivity. And how we understand this is that as you compress the structure, you're basically shortening the hopping distance, right, for the atoms to move and move through the crystal structure. So that's why we have an increase. In contrast, what you can see here, so here's conductivity again as a function of pressure and for a silicate melt. And what you can see is that as we increase pressure, we see the exact opposite behavior. You actually see a decrease in the conductivity. It's harder for the atoms to move through the system. Okay, what about the effect of volatiles on these materials? Well, it turns out, again, it's very different. So in crystalline silicates, you have, you incorporate volatiles into the crystal structure. Here's an example of water being incorporated into one of the olivine polymorphs. And so to be able to charge balance the volatile, what you have to do is you have to charge balance it by vacancies. So this effectively not only it expands out the structure, and then with the vacancies you also have a softer material. So what happens is you can, this might be a little bit hard to see, but this is bulk modulus or velocity as a function of water content, and what we expect to see is a decrease. So water or volatiles would soften a crystalline silicate. However, for amorphous materials, it's been shown that the volatile species can actually sit. So here we have our silica tetrahedra in the green and the red, and then here we have little blue hydroxyl units. And so what you can see here is that they actually can sit internal to these interstitial void spaces where they're not depolymerizing the structure. And so what's been shown is that when you have volatiles around, a lot of the work here has been done on noble gases, is that you have a stiffer response on compression than you would have in the intrinsic material. So this is an example for silica glass. Here's pressure, strain, you can think of it as volume. And the intrinsic material has a larger volume reduction than it does when you have things like helium or neon around. And the reason for this, what's been proposed, is that you have this big open silicate network akin to what we see here, and that the volatile species can actually go in and sit in these interstitial voices, reducing the volume reduction on compression. We also see a stiffer response when volatiles are around for velocities. So here's P-wave velocity as a function of density. And here's two examples for silica and basalt that I've measured. And the colored symbols are the intrinsic material response. And then when they're loaded with helium or neon around, you can see here that the velocities are much stiffer. Often you're getting the exact opposite response, right? Increasing velocities instead of decreasing velocities on compression. So again, we see a different response for amorphous silicates than what we would predict for crystalline materials. So at this point, I have to start asking myself, if every behavior is anomalous, maybe we're not describing the behavior very well at all. Maybe we need a new way to describe the behavior of these materials, right, at high pressure and temperature. And so for that, I've borrowed a lot on the work from Material Science and Martin Dove's group. And they have proposed that in amorphous silicates, there's this thing available that's termed network flexibility. So if we think about crystalline silicates, right, this is what I talked about earlier, where you have atoms that are bonded together, and how we think about this is that we're basically compressing the interatomic potentials, we're shortening the bond distances as we compress them, and so we get a stiffer and stiffer response as we reduce volume. However, because of the lack of long-range order in amorphous silicates, you have additional degrees of freedom. And the rigid polyhedra, in this case, can rotate relative to one another to reduce volume, and this is a very low energy way of reducing volume that doesn't actually compress the silica tetrahedra. The way that I think about this a lot, we've all seen these toys, right, where at science museums and things like that, where you have this big, this plastic ball that you can expand and contract just by the relative rotation of the plastic parts. Okay, so this is the mechanism that, we are proposing is active in amorphous silicates that can account for the wide range of anomalous behavior that we see. And because of this, crystalline equations of the state won't predict the high pressure properties for silicate liquids. Okay, so if I'm interested in measuring the properties of amorphous materials at high pressure, like I told you earlier, a lot of times traditional methods developed for crystalline materials like X-ray diffraction generally don't work very well. So I've had to use some novel techniques, some recently developed techniques, and today I'm going to focus a lot on density and the elastic properties, but I've also done some work on trying to measure the atomic structure in these materials to see if we can tell if network flexibility is active, and then also what is the influence on things like seismic velocity for the presence of silicate melts. All right, so to do a lot of my experiments, I use synchrotrons. I use the APS in Chicago. On my last postdoc, I had the opportunity to use ESRF and Soleil in France. It turns out the food's better at those synchrotrons than it is in Chicago. And fundamentally, just because not everybody works at a synchrotron, just a quick run through of how these things work. So there's a cathode that's heated to very high temperatures, generating electrons. Those are then, you use a linear accelerator to get those into what's known as a booster ring. And so here, the electrons are accelerated to like 99.999% of the speed of light. After they reach the speed, they're then injected into the storage ring, where there are some more nines after it to the speed of light. And when a charged particle is accelerated radially, then you get electromagnetic radiation, or X-rays. And so tangentially off of the storage ring, we have beam lines which basically just siphon off this electromagnetic radiation. It's very high energy X-rays, so we can see through things like aluminum or other metals that we use to contain our samples at high pressures. All right, so to measure density, normally with crystalline materials, right, you use X-ray diffraction, but there's no long-range order, so this becomes problematic with amorphous materials. So much of my PhD was spent developing high-pressure X-ray microtomography on the Jesse Carr's beamline at APS. And fundamentally, this is a large volume press. It's relatively small for a large volume press. It's about this tall. But it consists of opposing anvils, and in between, inside of a containment ring, we have some gasketing material, and then the sample goes into the hole right in the center of the gasket. Pressure is generated by applying a load on the ends, and there's only 2 anvils because in order to do tomography, we need to be able to see through at least a minimum of 180 degrees of rotation. So having opposing anvils gives us a clear view all the way through the sample. So microtomography is exactly like all the other types of tomography, where you take a series of radiographs and as a function of angle through the sample. For medical, right, CTs, you move the source, and here we actually spin the sample itself, which is something that makes this press, so unique. Once you have a series of rotational radiographs, you can then convert that into angular information that you can use to create horizontal slices that you then can stack and to construct a three-dimensional rendered volume. And so that's what we have here. This is actually a sample of silica. That's a little disk that we use to measure volume. So to get density, so this is volume. So how do we get density? Well, we start off by measuring the volume at 1 atmosphere inside the press, and then if we take incremental steps as we increase both pressure and temperature, we can measure the density as a function of these variables, getting a compression curve. Okay, to get at things like velocity, I use ultrasonic methods. So this is effectively the same as seismology. The thing that we measure here directly is the amount of time it takes a wave to travel through a material. So this is the setup. And what we do is we generate a acoustic wave that travels, in this case, through a buffer rod and then into the sample. And at every interface, part of the wave is reflected and part of the wave is transmitted. And so that's what's shown here, where we have the waves as a function of time. And so you can see the reflection of the wave coming back from the buffer rod sample interface, and then again from the far side of the sample. And so we can use this to tell us what is the travel time of the wave in the material. If we know the sample length, then we can calculate the velocity. So velocity is 2 times length over the travel time. And we do this at high pressure in the diamond anvil cell. And it works fundamentally the same, just instead of having the buffer rod connected directly to the sample, we have a diamond cell that acts as an extension of the buffer rod. And so we're looking for the signal between the diamond return and the far side of the sample. So velocities give us information about physical properties like the bulk and shear moduli. These are the things that seismic waves are sensitive to. And just as a little reminder here, so the bulk modulus is sensitive to both compressional and shear waves, whereas the shear modulus is only sensitive, the shear modulus is only sensitive to shear waves. The important thing here is when we're talking about liquids, we're really only interested in the P wave velocity because they don't support shear waves. So part of my NSF postdoc is working with Steve Jacobson at Northwestern because he uniquely has the ability to do gigahertz frequency ultrasonic interferometry. And so what I've proposed to do is develop the high temperature capabilities, and that's what's shown here. We're actually doing an experiment at 535 degrees C in the diamond cell. And we've moved it. This is where I overtook every instrument in Steve's lab. And it turns out his grad students don't like it when I do that. So this is a big part of the development, is to be able to push to higher temperatures. And just because this is such a unique instrument, it's the only one in the world that does gigahertz ultrasonic interferometry, I want to tell you a few of the capabilities that it has that are unique to it. So one thing is that it can measure velocity in opaque materials, and this is problematic in other velocity measurement techniques like Brion spectroscopy, where you're using lasers, because lasers would couple with an opaque material. It's also particularly well suited for velocity measurements in liquids and glasses. This is some of my work down here on silica, and this is looking at methanol-ethanol water going through the glass transition from where it doesn't support a shear wave to where you have a well-established shear wave. The other thing that's we're working on developing right now is the ability to measure the elastic properties of super hard materials. So one of the things that I am setting up to do this spring is to measure the elastic constants of diamond at high pressure. This is something that's never been done before. And I've been cutting little discs, laser cutting little discs of diamond at APS, and it turns out there's a function where you can put in text. So I wrote my name in diamond just for fun. Okay, so those are the techniques that I use to explore sort of these problems of silicate melts in the Earth. So let's get back to that. Let's talk about where are silicate melts in the Earth, and how do we know what is their spatial distribution and how much there are. Well, so right, there are places in the Earth where silicate melt is literally just leaking out. So we know it's down there. We also know from established 1D global average seismic velocity models such as PREM or AKF or AK135F, which is my particular favorite, that there are regions in the Earth where the seismic velocities are slower. So that's what's shown here in this red or in these curves here where we have velocity. So there are regions in the Earth where the velocities are slower than what we would expect for the average Earth. And the easiest way to explain this is by calling on the presence of silicate melts. But it turns out it's really, really hard to actually interpret the amount of melt present if we don't have a good equation of state for silicate melts at high pressure. So I'm going to show you results from my work and apply them to the lithosphere-asthenosphere boundary. This is a region in the Earth that has more or less a ubiquitous low velocity zone. And so how we normally think about the difference right between the lithosphere and the asthenosphere is that we have the transition from convection to conduction, right? The convecting asthenosphere and then the conducting asthenosphere. But if this was true, then seismic profiles through this region should be gradual if it's only a thermal gradient. So what we actually see, right, in many studies is that there is a sharp discontinuity, a lowering of velocity at this transition. And what's often called upon is the presence of silicate melts aligned in large sheared sheets that help lubricate the overlying tectonic plates so that they can flow relatively unhindered over the convecting mantle. So the velocity reductions at the LAB can be quite large. In the Western Pacific, there have been observed velocity reductions of about 8% at depths corresponding to the LAB for both P and S waves. Okay, so like I said, seismic velocities tell us basically how fast or slow something is. It doesn't really give us information on things like composition or phase. To really be able to understand these things, we need to, or what is leading to observed low velocity zones, we need to know things like what is the pressure dependence of velocities for melts. That will give us things like an idea of the volume we would predict and the melt geometry we would predict at high pressure. So what I've done, a paper of ours that is going to be published in mid-December in Science Advances, is trying to provide a new model for melt volume and melt geometry as a function of pressure in the upper mantle, and explicitly looking at things like coupling between the lithosphere-asthenosphere boundary. Okay, so we're going to go back here to our model of, or our data for P-wave velocity as a function of density. So again, at 1 atmosphere, remember silicate melts have this very narrow velocity range. In contrast, similarly, glasses at high pressure have a very weak pressure dependence. And so what I'm proposing is that silicate melts, although they're not exactly glasses, they're probably not going to behave more like crystals than like glasses, right? So what I do is I take silicate melt velocities, their properties at 1 atmosphere, and then I apply this weak pressure dependence that we see in glasses at high pressure to the silicate melt data. And what we can see here is that when we do that, we get significantly lower velocities as a function of pressure than has commonly been modeled in the literature. So here we have P-wave velocity as a function of depth. Here's our 1D global average model. Here's using a crystalline equation of state and the 1 atmosphere properties to be able to predict melt velocities. And here's using our very weak pressure dependence, right? So we're talking about, at the LAB, a 20% lower velocity and nearly a factor of 2 at the transition zone for melts if we use our model that's based on network flexibility densification rather than using crystalline equations of state. Okay, so how do I go from velocity to things like melt fraction? Well, to do that, I use Takei's model. So she constructed an analytical solution where you can take the observed seismic velocity to reduction, so that's what's shown here, these delta V's and delta S's, and calculate what you would expect for melt fraction. So that's what's shown here. So these equations are actually fairly simple. They really only depend on a couple things. One is melt fraction. This blue lambda parameter is controlled by melt geometry. And then we have this beta factor for the P-wave velocities, which is the ratio of the bulk modulus of the solid to the bulk modulus of the liquid. So what I've done is taken her model. Remember, it really only depends on these three parameters. So I've calculated the bulk modulus of our silicate melt here with the network flexibility model. Here's our crystalline silicate mantle, the AK135F 1D global average model. And then here we have the Birch-Murnaghan equation of state, predicted bulk modulus as a function of pressure for silicate liquids. And not surprisingly, right, the Birch-Murnaghan equation of state here sub-parallels the crystalline background mantle, and that's because we're using the same equation of state for both the liquid and the crystalline phase. Now remember, beta is actually the parameter that goes into these equations, and so here I just show you quickly the difference between beta for the Birch-Murnaghan equation of state, and because they're sub-parallel here, you can see that we actually end up with very low values in comparison, around 2, whereas the network flexibility model remains relatively constant here, and this has to do with the fact that we have these low, relatively pressure-independent velocities that we predict for the melt phase. Okay, so in this model, remember, we have a parameter for melt geometry. And so in my work, I look at 3 sort of in-member cases. So the thing that Takei's work really brings, I think, to the table and pushes forward is originally a lot of the work on calculating the effect of geometry on melt fraction had things like isolated melt pockets and flat disks and sheared, but these were all different studies. And so what she did is she created this thing, this aspect ratio alpha, that can describe the shape of the melt phase along a continuum. So we have things like isolated melt pockets to melt aligned in sheared bands or sheets. And then in the middle here, we have something that's more like equilibrium melt texture, where the melt is aligned along grain boundaries and interconnected. Okay, so I'm going to show you now the results of my calculations. We're going to start with S-wave velocity reductions as a function of pressure. So this is the velocity reduction, so larger velocity reduction going up as a function of pressure. And I have here the results calculated for the equilibrium melt texture. The results are generally the same for any melt geometry and sort of the melt fraction aspect. So what you can see here, and perhaps not surprisingly, is that it's the calculated velocity reduction is the same for both if we use the network flexibility model or the Birch-Murnaghan equation of state. And this has to do with the fact that we don't, shear waves aren't supported, right? So we don't really have a parameter that's dependent on P-wave or on the velocities of melt in the equation that actually gives us our velocity reduction. So here we have different melt fractions, 1, 3, and 5%. And what you can see, again, perhaps not surprisingly, is that as we increase melt fraction, we get an increase in the velocity reduction. Okay, so now let's look at what happens for our predicted P-wave velocity reductions. So here's the Birch-Murnaghan equation of state predicted velocity reductions. And what you can see is that, again, as we increase melt fraction, we get an increase in the amount of, or increase in the velocity reduction. But also what you can see here is that there is this strong pressure dependence, right, on the S-wave velocities, or the P-wave velocities, excuse me, as a function of pressure. In contrast, for the network flexibility model, what you can see here is that we have these relatively pressure-independent velocities that also increase with increasing melt fraction. And basically, what we have been predicting, what a Birch-Murnaghan equation of state predicts, is that you would become less sensitive, seismic velocities would become less sensitive to melt fraction with increasing pressure. And what the network flexibility model actually says is that pressure is not a big factor in controlling the velocity reductions, right? And this makes sense given that our model of velocities is weak pressure dependence. Okay, so if we take the ratio of the p to the S wave velocity, they're both dependent on melt fraction, phi over 2. If we take that ratio, we can isolate the effect of melt geometry. And that's what I've shown here. So here we have this ratio of melt velocity as a function of pressure. So we're going to start with the network flexibility model. And so here we have our three geometries, right? Isolated melt pockets, sheets, and equilibrium melt texture. And what you can see, again, perhaps not surprisingly, is that we have a very weak pressure dependence for this ratio as a function of pressure. In contrast, when we use the Birch-Murnaghan equation of state, we see that there's actually a very strong pressure dependence for this ratio of the S to the P wave velocities. So this means, right, for the network flexibility densification model, the only way to move between these values is to change the geometry. Whereas with the Birch-Murnaghan equation of state, right, the melt geometry, or this ratio is dependent not only on melt geometry, but also pressure. Okay, so let's look back at the LAB. Remember I told you that in the Western Pacific, there have been seismic observations that at depths corresponding to the LAB, there's about an 8% velocity reduction for both P and S waves. That means that we have an a ratio of S to P wave velocities of about 1. All right, so if we look at our melt geometry, it's pretty easy to explain these observed velocity reductions just with melt and equilibrium melt texture at the LAB. In contrast, it's pretty hard to use the Birch-Murnaghan equation of state model to explain the velocity reductions that have been reported in the Western Pacific. If we know the melt geometry, then we can calculate the melt fraction. And for about an 8% velocity reduction, we calculate that there's a maximum of about 4% melt. It's going to be a little bit lower than that because this model doesn't explicitly take into account temperature effects on the solid phase. Okay, so what does this mean for melt at the LAB, and what does that mean possibly for the dynamics of plate tectonics? Okay, so remember our sort of canonical view of how melts are, they're aligned at the LAB in these sort of shear bands that allow the plates to flow easily over the mantle. The problem is that we would expect a ratio of S to P wave velocities of about 2, and we don't see that. So what we actually see is melt aligned and equilibrium texture. Furthermore, in the Western Pacific, there has been geochemical observations for what's known as petite volcanism. And what they have been able to show is that the volcanoes, the volcanic systems are tracking with the plate motions. They seem to be very isolated, and so what they've proposed is that these are isolated melt ponds that are coupled or basically trapped between the lithosphere and the asthenosphere, which means that there's strong coupling, right, between the LAB. We don't have these large, sheared, interconnected melt films, at least not in the Western Pacific at the LAB. So now I'm going to spend a couple minutes telling you about sort of where I am going for the next little bit. So one thing is that I, as Jonathan said, have an NSF postdoc fellowship, and my proposed work is to work with Steve Jacobson and Anne Pommier to look at melts that are generated at the transition zone, hydrated partial melts. So again, one of those things about silicate melts is they're relatively difficult to measure experimentally, so we don't have a lot of data. So my goal is to measure at sort of 14 and 20 GPa the physical properties, so we can start to look at sort of the seismic work of like Brandon Schmatt and some other people that are saying that there's melting at the LAB and see if we can actually constrain what those low velocities are. And then this summer, I spent a chunk of time kind of thinking about where am I going after that. And it turns out that that my future may be in the Earth's distant past. Okay, so I'm interested in silicate melts. I'm also interested in things like what are the effects of changing composition, in particular volatiles. Remember the things that we saw about noble gases. How do they change the physical properties of silicate melts at high pressure? So I wrote a proposal for the Z machine in Sandia to look at how is water retained in planetary mantles during planetary formation. So one of the things is, right, as we look around us, everywhere we look, there just seems to be more and more water, right? There's water in the transition zone. There's water in meteorites. There's water in comets. We recently, I guess the Europeans, recently actually measured the water release from the comet 67P. And it turns out it has, it is a comet, but it has a ton of water, 1.2 liters per second being released into space. So, right, in the sort of canonical view of Earth's accretion and formation, we have this idea that because of the giant impactor, the Earth would have devolatilized, right, lost all of this water, and water would have been delivered later in the late Veneer, in which case oceans are probably a surface feature, right? And things that Steve Jacobson has been working on, and then also like Graham Pearson, where we're seeing water is coming from the transition zone. It suggests that there's more water in the Earth than we suspected. Also, there's some evidence from hydrogen isotopes which show that the Earth's water actually seems to be much more primordial in composition than comets. So this is some work from Altweg, where you can see here we have the protosolar nebula. This is the D to H ratio of the comet 67P. And then Earth falls intermediate. So this means that we're probably retaining some of our water from our early accretion. We didn't fully depolymerize the planet. And our intuition, especially from things, melts at low pressures, that you would devolatilize, the gases would go away. But what I'm arguing is that because of network flexibility, because you have this giant network that can basically collapse down in high pressure and store volatiles, possibly at great depths, being some of these early geochemical reservoirs. And so, as I mentioned, to do this work, normally I'm working at things that are maybe up to the transition zone, and now I'm talking about melts that are existing at the core mantle boundary, or perhaps even greater pressure during impacts. So that's the other thing. All of my work up to this point has been on static experiments, and so we're really interested in what happens for silicate melts during dynamic compression events. Okay, so this is the Z machine at Sandia. The summer we went there, it is enormous. The amount of resources that go into one experiment are just absolutely insane. There's 100 people that work on this just to set it up and tear it down every day, because you blow up basically a small bomb most days. And so hopefully we should be hearing back soon for this proposed work. And how the Z machine works is it's a shock compression device, but instead of using things like gunpowder, right, that's used in a standard shock compression experiment to accelerate a flyer plate, in this case they use the electromagnetic field. And so what they do, which is just mind-boggling to me, is that they take, well, first they use the current from the wall, which is insane, and then they store it in all of these capacitors, and then in a fraction of a second they dump 1,000 more times of energy than a bolt of lightning into this tiny area 20,000 times faster than an actual bolt of lightning. So most standard shock compression experiments, you're talking about maybe up to about 10 kilometers a second. The Z machine can actually achieve 40 kilometers a second for the velocities, getting to much higher pressures and temperatures than standard shock experiments. So with that, I've kind of taken you through where I've been and where I'm going, and I want to thank you all for your attention, and that's my talk. And a lot of people I work with.
Are there any questions for Alisha? I have a seismology question. Do seismologists see dispersion, like at that lithosphere boundary, they find that what of the velocity reduction?
So I'm going to answer that in reverse. Yes, I think it would be useful. To be fair, I don't know. These studies have been all pretty focused on absolute velocity reductions. And not being a seismologist, I just have to go with what they tell me. But there are some really interesting things that we can gain from other information. So one of the things, right, is seismic anisotropy. A lot of times people have attributed seismic anisotropy to the presence of melt aligned in bands. But there have been quite a few research groups recently. I'm thinking of a paper by Higgy et al. That maybe is like from 2015, where they're looking at ophiolites. So there's always an interesting thing because it's no longer in the earth. So what happened to it on its way up, right? But they basically find that there's a strong preferred crystal orientation, or lattice preferred orientation, which could account for the anisotropy void of these sort of large melt sheets. So it seems like it's not, our ideas are not, completely unreasonable given some other recent information. But I think dispersion could be interesting. Attenuation for sure. Melts are going to attenuate generally more than crystals. So, yeah.
I've got a question for you, Alisha. I'm wondering if your methodology can be applied to regions of active tectonics like mid-ocean ridges or oceanic volcanism to predict melt fractions underneath those.
Yeah, totally. So I am starting to work on trying to figure out, so one of the reasons I focused on the LAB and the Western Pacific is, I think it was 2015, Stern et al. Had the active source seismic study where they actually blew something up off of New Zealand. And that's the only way we really get P-wave velocity reductions usually directly. So because of that, they were actually able to say like, oh, there's an 8% velocity reduction here, right? Normally, again, unfortunately, I'm not a seismologist, so often when people are looking at melt areas, they focus on the S-wave velocity reduction. And so if I only have S-wave velocity reductions, then I can't constrain geometry, which means I cannot constrain melt fraction. But I do think that going into places, theoretically, this model should work all the way through the crust and the upper mantle, and probably into the transition zone sorts of pressures. We would expect this model to work as long as there aren't large coordination changes in the melt fraction. So that means that this should be sort of the densification mechanism. Yeah, this is same. Mm-hmm. So I think technically in the calculations by Martin Dove's group, they do have some things where they predict in their models a few different physical properties. Nobody's tried to measure it using sort of neutron methods. So actually, I guess along these lines, a big part of my postdoc in France, which I've cleverly hidden in the back, was on trying to measure changes in, we'll go here. So I was actually using X-ray diffraction to try and measure the atomic structure to look at changes in atomic spacing and simultaneously using X-ray microtomography to look at volume changes, all right? Here is intensity for X-ray diffraction as a function of Q. And we do Caesar X-ray diffraction to be able to pull out atomic structure information. And what Caesar is it's just combined energy and angular dispersive X-ray diffraction. So we're collecting what would be normally a crystalline data set, but we do it as a function of energy and angle. And then using Bragg's law, we can convert that to Q as a function of angle. We can stack these, normalize them a bunch of different ways, and then we end up with this sort of curve, right? And then from intensity as a function of Q, we can calculate the S of Q, which then can be, you can calculate the G of R, the pair distribution function. The important thing is that basically from this data, we can actually look at these peaks correspond to atomic spacing, right? So this is what I worked on. And so this is an example for instatight composition glass. And so here you have normalized volume, so the compression curve, density increasing down as a function of pressure. The blue curve here is silica. These dots up here are forced right, all cold compression. And then the green squares are my tomography data. And what you can see here, right, is that instatight composition is intermediate to forced right in silica. That all kind of makes sense on compression. But then when you heat it, you get this really large volume reduction. This is an 8% volume reduction at the glass transition. And we took Caesar diffraction patterns at these same PT conditions. I wonder if I have, oh, I'm missing it. Anyways, so the moral of the story is like we're tracking the position of like these different peaks for Mg SiO, or different magnesium silicon oxygen bonds. And so we have 4 different peaks, and what we see is that as we compress it and as we heat it, nothing moves. So the volume reduction is being accommodated by something different. Going into like, it's a little bit easier because of the even with things active like the rigid mode units, rigid unit modes, in crystalline silicates, you still have some long-range order, so it's a little bit easier to tell very minor changes. It becomes a little bit more complicated when your diffraction pattern looks like that. But I think it'd be interesting.
Is there an energy exchange during those volume reductions, like decrease or increase temperature?
So, what we know, I guess, from actually, and this is from velocity measurements, is that, so if we look at, I have a lot of slides. Okay, so if we look at like silica, right, we actually have the velocity decreases on compression. So I'm not 100% sure if I'm going to answer this, so please follow up. But the idea is that these are actually basically dynamic responses that require very little energy to compress the structure. Or reduce the volume, because you're not actually compressing. I guess the whole thing I've been arguing is you don't compress the structure. You reduce the volume.